In this video, we will present a feature of Paratie Plus that has been included to model some special retaining wall that are not compact but maybe have as a wall with internal slippage. This kind of wall can be considered as walls like U-sheet piles or staggered pile walls. So you can see here that in U-sheet piles the overall wall is composed by adjacent elements that are joined through a slipping joint, and this joint in U-sheet pile is along the neutral axis of the overall wall section, so some slippage may occur. And also sometimes this kind of wall can be considered for modeling the behavior of staggered pile walls. Let's first take a look of the most popular case, which arises when using Larsen sheet piles. Larsen sheet piles are very popular, and one of the most used steel sheet piles worldwide, because it was one of the initially proposed wall, and is sometimes appreciated also by contractors because they are quite rigid during driving operations. So driving operations are normally more straightforward than with other sections, can be easily moved at the side, and can also normally reused quite with efficiently. And it is also possible to compose special cross section with various configurations. And also the thickness normally is higher in the zone where their corrosion may be an issue, like in the corner like this. And this is typical with respect to other kind of shapes like AZ section, that normally the thickness is a little bit less for commercial shapes. Joints are joints along between adjacent wall, and normally do not interfere with the whaler beams and anchoring systems that are placed at the face of the element. And so there are many advantages, but of course there are severe limitations. The most important one, which is the fact that there is a joint between the neutral axis of the wall section, so it is quite questionable if this wall behaves like a compact section. And also, even if there is some restraints along the slippage, there may be some oblique bending, so the neutral axis actually is not as expected along the geometrical axis of the wall section, but there is a rotation of the neutral axis. So as I said, the main issues is to try to capture, to assess correctly the resistance of the joint slippage. The joint between Larsen single elements is improved if you drive elements in sandy soil before doing excavation. So in that case, the soil, some sand enters the joints, and the joints can be prevented to slip. But of course it is very difficult to calculate how much is the resistance. Normally you also may provide a capping beam or some intermediate elements when putting, for example, tie-backs, so that the slippage is also restrained in some points. And you may also, as some manufacturers propose, compose several elements and improving the resistance of the joint by crimping or welding the joint at some points. This must be negotiated with the contractor, of course. But of course, if you drive a sheet pile before and then you add a backfill like frequently occurs in maritime operations, when you drive the sheet pile, there is no soil, but maybe water only, and so in that case the joint resistance cannot be relied on. This is an important aspect that is highlighted, for example, in Eurocode in Part 5, steel piling. There is a thorough discussion of this aspect, and also there are recommendations to calculate reduced cross section of sheet piles. And as we will see, there are some reduction factors to either flexibility and resistance modulus of sections. As we can see, here is an extract of English national application document that gives some recommendation for such factors. These factors are normally used when, must be used when calculating the flexibility and checking the resistance of such pile. Must not be forgot. As I said, Eurocode also recommends some values for in case of crimping adjacent element. So in that case, of course, crimping must be provided before installing the piles, and must be also checked and proved by laboratory or on-site tests. These are normal figures that one can take into account to calculate the joint resistance provided by crimps. From the mechanical point of view, we see in our opinion, this kind of the Larsen walls may be considered very similar to what happens when you do a tangent or second pile wall and you provide some offset in normal direction to the wall midplane in order to provide some additional stiffness of the pile or the pile wall. In that case, in a situation like this, the wall is more rigid due to the geometrical effects due to the, how to say, the improving of including some lever arm between some elements. Of course, this wall works as a combined wall if the single element can share shear forces along the joints. So what happens in a staggered pile wall? Normally there are these situations. These are the forces acting. In blue I highlighted the lateral pressure of the soil from the driving side and from the resisting side, that are the same loads that occur in a compact retaining wall. Then the outer and the inner piling rows are all subjected to a mutual interaction that can be provided either by the soil in between piles or by the grouting that interfere from each pile to the other piles. And if the distance between the two rows of piles is big, there is also a resistance due to the each pile acting as also a vertical loaded pile, and we may have a base resistance if the pile is in compression, and also a shaft resistance. Well, while the blue and the black action can be somehow modeled and captured by a program like Paratie Plus, of course, if the behavior is also dictated by vertical behavior of single piles as vertical piles, a more advanced numerical model is normally required. These are the criteria that can be used to determine the possible resistance and stiffness of the connection between adjacent piles. Of course, if the piles do not interfere, you may not have slippage mutual resistance at all. But if they do interfere like this, what we can expect is that the shear resistance is given by the resistance provided by the grouting around or the cement that compose the pile. How we then can model this with Paratie Plus? We have two ways. One way is, as I briefly mentioned, is to consider an ordinary wall and taking into account the beta factor suggested by Eurocode. But we have also included a different element that is a special wall element in which internal joint behavior is included within the wall element. So we have an element that may act as two single walls that are mentioned here like unglued elements, or as another upper bound value as a fully compact section, so accounting for the inertia of the cross section as a wall, or we may also capture a flexible connection behavior that is in between the two lower and upper bound behavior. We call this element C-wall element, combined wall element, and this element is composed internally by two elastic beam elements that we call legs, and one continuous interfacing between such two legs. And to describe the behavior of the element, it is also necessary to activate an additional degrees of freedom in the model that we call slippage S. And in this brief sketch, we see the kinematics of the element at each node. So the two internal nodes of the two parts share the same displacement and the same rotations, but they may have a slippage, a mutual slippage between the two elements. Doing so, we can describe the behavior of such element. By the way, a way of thinking like that is often used in many finite elements provided in other programs. For example, for those elements that can model the warping behavior of beams. once this element has been used, the results are not only the overall bending moment and shear force of the element, but also the shear, the internal action taken by each leg, and also the joint force along the wall. Just to remember that the joint force is joint behavior is plastic, and if plastic occur, we may have also plastic slippage. To assess the capability of the element, here you can show a simple numerical experiment in which we took a cantilever and we applied a uniform load, and we see that if the stiffness of the joints is very low, the solution is asymptotically equal to the solution of corresponding with the bending inertia of just the sum of the inertia of the two legs. So we may have a deflection calculated by these formulas. Whereas on the opposite side, if the inertia is the stiffness of the joint is beyond above a certain value, we have the cantilever, the bending deflection of the single of the cantilever as a whole. In between, we have a smooth transition zone in between the two elements. And here also we can see the compression strength for various situations. Of course, if the element is compact, we have the maximum. If the element is compact, here we have the minimum compression stress. Whereas, of course, if the element is fully the joint is fully loose, we have the maximum situation where compression stress occurs. And then here we have some intermediate value depending on the stiffness. We can check this behavior going into quite realistic example, and we took a PU28 sheet pile that is normally recommended by many manufacturers, and we calculate the bending behavior of a cantilever sheet pile. Here you can see what happens if we modify, if we model the joint resistance, including the crimp stiffness and resistance recommended by Eurocode. We can see that if we crimp the wall at each two joints, we have the maximum deflection. Whereas if we crimp, as recommended by Eurocode, the wall at each joint, essentially we have the same behavior of this cantilever beam as modeled like an ordinary beam element, and including a reduction factor beta D equal to 0.55, that is in the range of recommended value. So the element is essentially capable to reproduce more precisely the behavior of sheet piles as recommended by Eurocode. And here you can see what are the results. We have the overall bending moment, of course, and this is the moment in a single leg. Whereas here we have the bending moment, the axial force in each of the two legs. Due to the formulation of the element at each cross section, we have a couple of equal forces but opposite in sign. So it means that one leg takes compression and one other leg takes tension. This is also demonstrated by Paratie plus. And here we have the distribution of shear force along the joints. Of course, we can see that more or less, this complies with the shear force distribution like a beam, because here we have almost a zero strain, and here we change in sign when we have the maximum bending moment, like said by normal theory of structures. Again, here we can see how we calculate the stresses internal to the elements, and we can see that depending of the assumption of the joint, we may have a fully compact behavior, so the stresses along the overall cross section are essentially linear. Whereas if we have a deformable slippage, we have a behavior that is in between the two. Essentially, the maximum values are the same, but internally the axial stress in these 2 points are quite different than assuming compact behavior. And this also is in agreement with available data in the literature. Here we show an example of a study proposed by Byfield and Mower in the Journal of Construction Steel Research. Here we see that these are the same behavior of stress pattern observed in numerical data. Of course, that example was the results from that example stem from a laboratory test of a wool model, but of course this shows that the element has the capability to model the expected behavior. So our element, in our opinion, can be useful for essentially 2 purposes. To determine the design actions in the connection between elements if you want to weld or crimp the elements, and compare and validate models based on classical approach. So you can always use the classical approach, providing beta D and beta B factor and norm ordinary beam element, but if you are not familiar or confident with that value, you can also try to figure what happens with the seawall element. Just to summarize, we see some seawall features. Most important, of course, the vertical connection that governs the seawall behavior is totally fall under your control, and in this respect you may also decide when activate this slippage. For example, you can also omit the joint slippage internal to the element, but you can add later on during excavation analysis some special elements that fix this slippage at some points along the wall. This just if you want to, for example, to model welding after excavating and before going on with an additional excavation. And of course you can also decide that in one part there is some resistance and in another part a different resistance by simply subdividing a wall into several segments. And if plasticity occurs, you can also appreciate the plastic joint resistance given by Paratie plus. Finally, there are of course some limitations in this element due to the formulation of the element. If in a model you consider seawall element without any joint stiffness and you don't restrain at least one level with a slip resisting boundary condition, the model is has an internal instability, so it is you may have a zero pivot in the analysis, but of course this is a situation that is quite theoretical. Normally there is no, this problem is not highlighted. And according to this, if you don't consider slippage along a wall and simply restrain one level, the coupled behavior is not activated. So the two walls act as separate walls. And moreover, such elements cannot be added connected to slave nodes. And what I recommend is that once you decide to use seawall elements, it is better not to mix this element with the ordinary beam elements, because of course it works, but the results assessment may be a little bit difficult. You may have some questions to understand how the equilibrium is respected. Even if it is respected, but it is not quite apparent how the results are shared. And at the moment, such elements are not checked automatically with our reinforced concrete program or steel structure program. We will plan to include this feature also in next release of the program. If you want to check and have some question, you may contact us at this address, or if you are in Italy, with our Italian agent, that is ARPA Chairs. Thank you for watching the video.